So now I'll talk about different project, completely different project. So, and I'm standing for Belaineh, who is on a project meeting in Barcelona right now. And the name of this project is GREENSENSE, and here we're trying to use nanocellulose as a biosensing platform, and we are trying to detect drugs of abuse. And the overview is this is a Horizon 2020 EU-funded project, which has 12 partners. So it's mainly guided by LATAT in Spain, and Genes Inc. from France. I mean, there is Melodia from Israel. So it's a highly collaborative work with multiple partners, a lot of meetings, and a lot of inputs from all different backgrounds and countries. So the big background to this study is that we are losing a lot of people, thousands, tens of thousands of people due to drug abuse. And here I'm showing the drug-induced mortality rates among adults, specifically for Europe. This is a bit old, from like 2014, but we see that it's constant, even though we are progressing as a society and technologically. And specifically for Sweden, we had a slight rise, I think around 2014, but it's dropping now. But it's a reason for concern, and it's a global issue. So we see, based on different societal, political, or economic issues, we really have a high rate of drug abuse, where we lose tens of thousands of people every year to drug-related disorders. And specifically in the US now, there is this opioid crisis. So in 2017, the US Department of Health actually declared an emergency. So it's really a case for concern, and it costs a lot of money. So we're talking about hundreds of billions of euros or USD. And why are we still losing life? So diagnosis of drug intoxication is complex. So here I have what is called a toxidrome, so which shows the different kinds of drugs and the different symptoms. So this is the physical symptoms. So heart rate, respiration, the temperature of the person, pupil dilation or constriction, and a lot of things. So there are overlapping symptoms, and what complicates things are that drug consumers generally take multiple drugs. So it's almost impossible to figure out at the emergency room to figure out what a person took. So, and especially if the person has overdosed. So there is a need for on the point, so point of care tools, which actually tell us what the person has consumed. And this has to be fast, it has to be reliable, and it has to be environmentally friendly. So that's where cellulose, or this GREENSENSE project, comes in. So where we want to use cellulose imprinted electronics for healthcare diagnostics and as a biosensing platform. So we want to have in this system energy autonomy. It should be able to communicate wirelessly, because I mean the doctor is treating the person right there, and if we want to transmit the data for information, it should be also easy to use, and the results should be readable by anybody in this world. So it's a global issue, so it should be as simple as possible. And maybe this slide is not necessary. We need nanocellulose for sure, but simply we have lower costs, and the environmental impact is huge. So far the disadvantages have been poor compatibility with printing processes, which we have overcome now. And we have this list of, even longer list of benefits: strengths, high aspect ratio, transparency, low porosity. And what we also really like is that we can modify cellulose chemically and structurally in a multitude of ways, I think, as Mohit just showed. So the plan is use nanocellulose, use it in films and inks as a component actively or as as an additive, use it in printing. So we basically print electronics for near-field communication, for the display, for the energy storage, so which means we can also use the power paper material in the energy storage for these devices, and also as a biosensor, as part of the biosensor. So experimentally, we do a lot of material development, which means, so I say, poor printability or compatibility with printing processes. So what we try to do here is put the cellulose in different kinds of solvents, which should be printable, which should also be hopefully food grade certified so that they are not toxic. So we tried different kinds of solvents and also different kinds of ethyl cellulose. So we tried a range of celluloses, polymeric cellulose, and here we try CNF, which is nanofibrils, and CNC, which is cellulose nanocrystals. So we go out basically and try a range of structural and chemical variations of cellulose. And as an example, so we applied it as an active component to make a conductive carbon ink. So previously we had trouble printing large-sized, thick films of carbon. And now by adding a certain amount of, so here CNF, like around 3%, we can actually get quite reasonable resistivities and basically conductivities, which are comparable to numbers that we get from other commercial sources. But here using, for example, carbon, which has been sourced from natural sources, and also cellulose as an additive to improve printability. And another application is to use it in supercapacitors. So that has been already shown. And also use it in electrochromic displays. So we use the ink in electrochromic displays, and we show that, so C1 and C2 are the two process inks that we developed at RISE. And so this is progressive. C1 actually is made later. And we see that, so here is an electrochromic display where we see the contrast between off and on, or off and on, depending on which voltage you're applying. But we see that we can get a high level of contrast between off and on for the inks we made. And we also wanted to further develop the electrolyte. So we have the substrate, the electrodes, which we have been working with. But now we also want to make the cellulose part of the electrolyte. And the electrolyte, it basically has to be insulator to electronic charge transport, and it has to be high ionic conductivity. So basically we need cellulosic materials with the chemical configuration that allow us those two parameters. And we tried a range of materials here as well. So a range of cellulose nanocrystals, cellulose nanofibrils, and another cellulose nanofibrils, which we call Gen 5, which has a different chemical modification. And basically we can get printable, so these are the electrodes, so the electrochromic displays printed, a very good printability, and we actually narrowed down our material to a short list. And this is basically a summary of the yield per material, and also like here we show that, I mean here we're using quite low amount of material, so 0.3% in wet state and maybe 5 to 10% in dry state. So, but we still get, by using cellulose that of different kinds, we can improve the contrast of our displays. And here we have a demo of one electrochromic display. Is it already on? I think it's already on. Yeah, so it's already on. So it's on a substrate of cellulose, which is transparent, and I can play it again. So by accessing the two sides of the electrodes, we can switch on and off the display. So here we are using the CNC as a substrate, or here the CNF. So we can make transparent, completely transparent substrates based on cellulose, which for displays is a must-have. Sorry, this continues. Basically, we are printing on semi-large scale. So this daisy chain chips, which can be used to detect defects in circuits. So this is comparing a plastic, which is PEA, I think, PET here, and cellulose. So basically, we can go down in resolution to like, tens of microns, which is quite similar to what we also can get in PET. So we can completely substitute substrates with cellulose-based substrates. So overall, the plan is to use nanocellulose in all parts of this sensor material. It could be a substrate, it can be an active material, it can be an additive, it can be a structural support. And we have basically come up with manufacturing these devices pretty much by using cellulose in almost all parts of this device. And yeah, that's it. And thank you for your attention.